Hi, so quick guide on how to use Microchip's 128K I2C EEPROM. Costs about 30 pence from element 14 straight Farnell. 30 pence. This is 128K. The one on the Fusion board, which I've been using. That's 128 bytes of data, whereas this one's 16,000 bytes of data. So I mean, if it's a shame, you know, Microelectronica built that EasyPick Fusion 7, used colour TFT display, and I don't know, for an extra 10 pence they could have put a decent sized chip on there. What a shame. But anyway, so I've got an external EEPROM. That's 128K, 16,000 bit locations. So using 16,000 bits, you're not going to find an address using an 8-bit configuration. What I'm doing here is writing a 20 to this address at the moment. That's just a normal child can 0 to 255. When it gets to 255, that's going to roll over, and J is going to increment by 1. Once that happens, we've then got a high address at 1, and then it's going to go to 255, 0 to 255 again. So we've got another 255 bits. Now we'll go to 2. When this does roll over, when J is equal to 1, I'm changing the data we're writing to 40, and then when it equals 2, I'm changing it to 60 and 80, so on and so forth. So that's going to roll over in a minute, so I'll leave the camera on it. Just want to show you that I'm actually writing the data first. I'll show you the wiring diagram and the code. So here Microelectronica have 10 English pence and stick a decent EEPROM chip on your board. Right, that's about to roll over. Put my change away. I've actually had to speed the clock up on this PIC. I'm actually using a PIC 32. There we go there. I've had to speed it all up because putting this text on this large screen slows everything down. Otherwise, yeah, the numbers would be too fast. If I delete all this text, you wouldn't be able to see the numbers counting. They'd be so quick. So obviously that's gone past 255. J is incremented by 1, so now we've got another 255 addresses to write. They're not the same previous addresses because the address has changed. This has gone up by 1. So writing the second lot of 255. And you keep on going until you get to, actually I have worked it out and I'll show you in a minute, 16,384, which is hex 3FFF. Right, so while it's putting some 40s to this second higher address, I'll show you some drawings so you can see the configuration. Right, this is what I've drawn. This is the chip. I haven't actually marked the pin numbers. Pin 1's here, 4, 5, 6, 7, 8. Where do I start? So I suppose the confusing bit are these first 3 pins, A0, A1 and A2. A is for address. So you can have up to 8 devices on one, say one board, and the microcontroller can look for a certain address and either write or read to it. So the idea is you have these three different pins, and you can either connect them all to ground, in which case the address would be 0, 0, 0, connect them all to 5 volts or 1.7 to 5.5, in which case it would be 1, 1, 1, or any combination of those 3. So that could be high, that could be ground, that could be high, those 2 could be high and that could be ground. With the permutations you get 8 different addresses. So you've got to be careful where are you connecting these first? Obviously VSS is ground, VCC 1.7 to 5.5 volts. Write protect. If you want to write to the chip, you have to ground it. If you don't want to write to the chip, you want to protect it, you have to pull this up to 5 volts. And then serial data, serial clock, and data sheet from Microchip. Download it, have a look. You have to use a pull-up resistor on this serial data line. It's an open drain, so they recommend 10k if you're running 100 kilohertz, down to 2k for up to 400 kilohertz. So that's that drawing. Hopefully you can see it all. Right. So this is what I was explaining about the address, which you need to know what pins you've connected where, because you'll need to know the address to start writing and reading from the chip. So yeah, the quick example, if A0, 1 and 2 are ground, the slave address is 000, this bit here. The control code is these first 4 bits, 1010, and they always remain at those numbers. So that's the control code, that's your address. And just to the right there, that's the same control code, 1010. If you tied those 3 pins, these 3, 1, 2, 3, if you tie them all high to 5 volts, the code's going to be 111. So control code and chip select. And you'll notice we've got another bit here, was it read write and read write. So depending on what you're doing, these numbers here, or that bit alters. So I've written it all out for you. Make sure you're on the screen. So if you want to write to the EEPROM, that's the control code, 1010. If all the pins are tied to ground, 000, and 0 is for write without spaces. So that binary code is actually hex A0. So, and to write to the chip, you go using I2C 10100000, the high address, then the low address, then the data in, so the bit the byte you want to write, and then stop. That's how you write to the EEPROM. And then scrolling down, a bit more difficult, but so the read, still the same control code, same address, depending on if you've got them tied high or low. And then see this write here, so you're writing to the EEPROM, writing what address you want to read from. So the high address, low address, you restart the I2C, put the same control code in, the same address, chip select, and you put a 1 here, so 1 is for read, then the data out, that'll be your data out, the 1 byte that you're reading, and then stop bit. There's no acknowledgements, you don't have to use the acknowledgement on the I2C with this chip. So that's about it. You see I've done it today, 10th of March. This is a quick rundown for beginners. So the first address for all the low capacity EEPROMs, you've only got, if you've got 8 bits there, well they go 0, 1, 2, 3, 4, 5, 6, 7, but 0's a number. You've got 255 spaces, so you can only get 255 different addresses. But what happens when it rolls over, you can increment this by 1 and start again. And if this high address on this particular chip just uses 6 bits, to give you 63 spaces, or 63 in digital. 0 to 63 is actually 64 because 0's a number, so 16,000 locations using that configuration. Actually 0 to 255 is actually 256, 0 to 63 is actually 64, so 16,000, or 64 times 256, 16,384 bits. And from the data sheet they say the EEPROM rolls over at hex 3FFF, which is decimal 16383. But remembering naught is a number, so 16383 is actually 16,384. That's it. That's how you read and write to the chip. Right, here's my code, standard setup for the 5-inch TFT I've been using on the last few videos. That's the initialization. In case you haven't seen the other videos and you've got 5-inch display, copy that and you get the correct colours. This is the EEPROM. There's a simple demonstration on Microelectronica's site. I've just used that and modified it to suit this bigger chip. So what I've done, this is W is for write, address, and that's it, ended. So I've just called it write address high and write address lows. I've added one line. So as the small address EEPROM, you only need to write one byte for one bit of address. So unsigned char, they're all chars, they don't go over 255. Obviously the 255 is going to keep on going round, and it's going to increment the other one by 1, and the other one only goes up to 63, 64, so that doesn't need to be an int, that's a char as well. So unsigned char for the address, write address high, write address low, and unsigned char for the data, because we can only get a byte out at a time. This is a bit I've removed. That was the standard write single. You see there, the AO is a control code. So let me just show you. Pull up the calculator. For those of you who haven't seen the other videos, I don't normally put it in the screen as well. Right, so control code 101. Actually, for those who haven't seen, I haven't put standard Windows calculator. View down to programmer, down to binary. So we know the control code 1010. If we tied our 3 address lines to ground, that'll be 0, so 3 more zeros. 1, 2, 3. And for writing we just use another 0. So convert that to hexadecimal, that's our AO. So you see at the top there, that's our standard write single. Write the control code, write the high, write the low, and then the I2C write is the W data. That's the data you're writing, and then stop. Right, and then reading, slightly more difficult, but easy once you get the hang of it. So same again, unsigned char for address high, address low, and then char as a result. The result is the data being read from the EEPROM. So I2C start, our control codes are A0. We tell it we want to write to the address high and the address low, and we restart the I2C, and then this is, it says it on the data sheet, we then need an A1. So if you just work that backwards, pull up the calculator again. So we had an A0, so I know this A0, the difference between A0 and A1 is going to be a 1 at the end. So if I go cancel, back to binary, control code 1010, chip select or address 000, then I know we're going to put a 1 there for the second part of the read. Convert that back to hexadecimal, A1. but it's all on the data sheet. I'll just pull it up. So that's the data sheet for the chip I'm using. I can quickly scroll down. One important bit of information I forgot to mention, I think I did have it on a picture. If you're using the micro small outline package, some of these pins aren't used. I think you've only got a choice of 2 addresses. You can't use all 3. So if you're using the surface mount MSOP micro small outline package, forget 2 of these because you can't use them, but it's all in the data sheet. Have a read. It breaks it down there. So byte right, so start, control byte, that's the address, depending on if your pins are high or low. And then look, we put a 0 there to write to the EEPROM. High byte, which is only 6 places, low byte 7, 8 places, and data out and stop. Page right, have a read if you want to start writing 64 bits at one time, 64 or 63 bits. That's page right. So if you're just reading individual bits, you've written something and you want to go and read a specific address, that's called random read. So this is the start, control byte, the address, 000, if the pins are grounded, that's our first read write bit, so we're writing a 0, address high, address low, restart, control code, chip address, and then the 1 there. So that was our A0 and A1. Sequential read is if you want to read loads of data at once. You can just put the control byte in there and read a string of bytes. These are the I and J are for the addresses. And then data this is the data we're going to read from the EEPROM, and it's a string converting it so I can put it on the TFT, and then like I string for the conversion, J string conversion, X2 is for when I start plotting stuff on the TFT, and this is a char, so char anything, I've called it anything. I was writing a 20 to the EEPROM. And then converting that anything to a string just to write it on the TFT. So initialize the MCU, initialize the touch panel. This is initializing the I2C, or 1 in this case, 100,000 Hertz, and then I'm filling the screen. And this is, can't get you zoomed, okay, zoom you in a small bit more. So this is a loop I'll start with. For I is 255. For I equals 0, so hex 0. I is less than 70, that's 2000, just to give you an idea. We're writing more than 255 bits, so that's just a random number, is 2000. Then I plus plus. If I is equal to 255, when I rolls over, I address increments by 1, so when it gets to 255, I equals 0, and J plus plus, so J increments by 1. And these are the bits of data, so I can show you when we read it back. If J is equal to 1, anything equals to 40. If J equals 2, anything equals 60. If J equals 3, anything equals 80. So then this is the EEPROM write single, I, J. So remember it was I and J. So where's their write? So high address first, then low address, and data in. So EEPROM write, high address, low address, and anything. Then these are just the conversions, your byte to string for the TFT. That's our text. I'll put this text on there to show you what I was doing. Right, I've removed all the writing code and just put a simple read single data, taken off the text, and you see it's rapidly speeding up. Putting text, your large text on the screen just slows everything down. So this is I, this is J, and this is the data being read off the EEPROM. Remember, we go to 20, 40, 60, 80 when it gets to 1, 2 and 3. So I has just rolled over, J is equal to 1. Now we're reading the next 255 addresses, which is 40. See, if I deleted this, then that would speed up even faster, probably be too quick for the EEPROM. This is why I changed the write it in one colour and write it again in yellow, so it clears the numbers so you can still see it. You see it's rolled over again, J's become 2, we're going up to 60, and there's not enough room on this screen for the 80s, I don't think. Ooh, I don't know, are we going to catch it? Yes, just. So that will just keep on going. Obviously I haven't got a running total of what address we're on, but that loop, as you remember, is going up to 2000. So that's it. So first 255, second 255, third 255, all the way up to 16,000. I'll just change the code just for that other command you saw, which is instead of reading with EEPROM, instead of writing, just EEPROM read, where we start, put the addresses in, and restart and read it again. So that's it. Hopefully you found this simple. Obviously storing data, you can obviously print it back out, find out what's been happening. I specifically want this to record 12 hours of data, 720 bits or 720 bytes of sunshine from my solar panel. You might have seen the other video. So that's why a little EEPROM on this Fusion board with 128 bytes was not much use. So that's how you read and write to an EEPROM with a larger memory, and obviously you need 2 address bytes. Hope you found this helpful. Thank you very much.